Let's check out lesson 4, Earth's energy flows and factors that affect them. So check out this picture here. It says solar energy input to Earth's surface on average is 342 watts per meter squared. So that's represented by those wiggly yellow arrows. Heat flowing out of Earth's deep interior is much smaller, only 0.06 watts per meter squared. So yes, there's actually energy, thermal energy coming onto our planet from deep within Earth's core. So we often forget about that, or I do at least. And then last, it says to maintain a constant temperature, heat radiating from Earth must balance solar input, right? Because if we just kept absorbing the sun and never releasing any of it back into space, we would have all been gone long before now. So it says, has the surface of Earth maintained a constant temperature in recent years? No, it hasn't. I guess there's not any real way of knowing from this picture, but based on what we know about how the average temperature of Earth has gone up, we know that it hasn't remained a constant. Okay, so it's kind of a simple question there. Question 2, look at the two graphs shown below. The one on the left shows radiation emitted from the sun, while the one on the right shows radiation emitted from Earth. What do you notice? Fill in the blanks. Well, the solar radiation, so the energy from the sun, falls mostly in the visible spectrum. That's where it peaks right here. And the infrared. All of this is in the infrared. There's a little bit that falls within the ultraviolet right there. Okay, and then the rest is in the visible. So it actually looks like most is infrared spectrum, while energy output from the Earth falls entirely within the infrared spectrum. So what does that mean? The sun is constantly giving off energy, and it arrives to our planet as visible light. Some of the visible light is reflected back to space, but some is absorbed by Earth. The Earth radiates this energy, which is no longer visible, and is called infrared radiation. Because of the greenhouse gas effect, the infrared radiation has been taking a longer time to leave Earth and return to space. Okay, so how exactly do greenhouse gases come into play? Let's watch a YouTube video to look at how infrared radiation interacts with air, a mixture of mostly nitrogen, oxygen, carbon dioxide, and argon, and contrast that with carbon dioxide and contrast it with another gas called tetrafluoroethane. And then a couple of questions that come first, just to double check from the last lesson. Nitrogen and oxygen are not greenhouse gases. They did not wiggle in that simulation where we fired infrared photons at them. Carbon dioxide is a greenhouse gas, and this is new information. Tetrafluoroethane is an extremely potent greenhouse gas. Okay, so let's take a look at this YouTube. Okay, I guess I need to click on it again. Of course, there's an ad. I'm sorry, I had this geared up. Oh, it is geared up. Okay, it's right here. I just got confused because it said pivot. So I'm going to make this big. I have no sound on this. So here's obviously just a regular camera, and down here is these kids with an infrared camera, and there's 3 plastic bags they're holding in front of their face. The first one's filled with air, the second one in the middle is filled with carbon dioxide, and the third one is filled with tetrafluoroethane. Okay, you can really see something dramatic is going on there. So visible light goes through all of them, but infrared radiation acts differently. Because all the 3 faces are warm, they emit infrared radiation. So the highest is when it's that yellow color, and then the coolest is like that dark, dark purple color. Different gases block different amounts of infrared radiation. So the least and then medium with carbon dioxide, and the most is blocked with tetrafluoroethane. So, and then it says absorption of infrared by atmospheric gases is a key component of the greenhouse effect. Okay, so let's make sense of this. What conclusions can you draw from the video? Greenhouse gases absorb infrared radiation. This means that when infrared radiation is trying to leave Earth, the growing amount of greenhouse gases in our atmosphere is preventing it from leaving, which ultimately results in a warming effect on our planet. And then definitely check out this Futurama clip, pause the video, because it's like a cartoon explanation and it's really funny. So pause this video and watch this. Do it. Okay, then let's take a look at this basic model of Earth's energy budget story. Okay, it's kind of just a click through. So first, energy enters the Earth system from the sun. Some is reflected off of clouds, dust, other particles, and never even makes it to Earth's surface. Most of the energy, though, does get to the surface, where it is absorbed by the ground, trees, everything around us, buildings. There are some parts of Earth's surface, though, that are really reflective. Ice, like a glacier, snow. So while most of the energy is absorbed, there is a certain amount that bounces off, reflects, and heads right back into space. And then this visible light that was absorbed, now it's emitted from Earth's surface. But most of it is stopped along its way out. So clouds and gases, like we learned, carbon dioxide, absorb this energy and it can't escape. Only a small amount directly escapes. Energy emitted from those clouds and gases goes in all directions. Some comes back to further warm the Earth. That's called the greenhouse effect. Finally, it says the surface energy budget is balanced by thermals and evaporation. Together, all of these forms of incoming and outgoing energy have resulted in just the right living conditions for us on Earth. Scientists use satellites, ground-based instruments, aircraft field campaigns, and computer models to determine the magnitude of each flux, which is, you know, the changes in where the energy is moving. That's the flux. And so they put values on this. It says all flux values are shown are in percentages and are based on 10 years of data. And this was outdated right here. It's 2009, but it's an amazing set of graphics. Notice this, net absorbed, 0.2%. So in a perfect world, this would be 0%, because the same amount that we're getting would be leaving, but we're absorbing more than we're releasing. So that's called a positive imbalance, even though it's not a positive thing. And let's see if there's anything else, any other details from here. Let's read this. Earth's energy budget describes the various kinds and amounts of energy that enter and leave Earth's system. It includes both the radiative components, light and heat, that can be measured by CIRRUS, a high-priority NASA Earth System Measurement Program, and other components like conduction, convection, evaporation, which also transport heat from Earth's surface. On average and over the long term, there is a balance at the top of the atmosphere. The amount of energy coming in from the sun is the same amount going out, and from emission of infrared radiation, IR, or heat. Okay, except lately, it's not balanced. Okay, so this was in 2009, and they were already measuring that Earth's energy budget was not balanced. So that's kind of the takeaway from this. All right, so let's start sketching some models here. So it says, sketch your own model of the energy flowing to and from Earth. Be sure to consider energy inputs, energy storage, and energy outputs. Your model should include the sun, space, Earth's atmosphere, and the surface of the Earth. Use arrows to show the different types and amounts of energy. Use yellow arrows to show visible light and red arrows to show infrared radiation. Okay, so let's draw some yellow lines first. We've got the energy coming in and lots of it bouncing off of clouds. And then we've got some coming in and some reflects back to space from hitting ice and snow and things like that. And then we've also got some that's escaping that's been converted into infrared radiation, and then there's some that's bouncing around because of the greenhouse gas effects. Is this just supposed to be, okay. There. All right. And then it says, draw your model again, but consider what the amounts of energy would look like before the Industrial Revolution. There were no factories or cars. So, okay, we would have energy still coming in and some reflecting off this. And before there were cars, we wouldn't have as much bouncing around, maybe like one bounce and then it's out. Here I kind of bounced it around a little bit more, but there weren't as many greenhouse gases, so it could escape faster. Now it says draw it again, but consider what the amounts of energy would look like if global CO2 levels are allowed to continue to increase. Uh-oh. Okay, so we're still going to have some hitting clouds and some leaving here, but the energy that is converted into infrared is going to bounce and bounce and bounce around and stay in Earth's atmosphere longer. This is like obviously an exaggeration, but it's going to stay much longer. And then what would the amounts of energy look like if Earth had no atmosphere? Okay, so it would bounce back into space, and anything that was turned into infrared radiation would also just leave. So just like that simulation, it would be very cold. Okay, it says in the diagram on the right, label the following: Earth's energy input. Okay, that's the energy coming from the sun. Here and here are those arrows. Earth's energy output is here, and it looks like here, even though they're bouncing around from the greenhouse gases, these arrows are all representing the infrared energy leaving back into space, infrared radiation. And then energy storage and redistribution, this is shown here. Winds and ocean currents move heat energy within the Earth system. Okay, and then if you are doing this outside of class, in class, we actually moved everybody's bodies and acted out these scenarios. So people were light energy, and then they converted into thermal energy once they got to Earth's surface, and sometimes they got trapped in the atmosphere and were bouncing around. There's a good video showing this. Oops, there's a link on yours off to the side to kind of watch. So you're not going to see all 4 scenarios unless you're there, but go ahead and record your biggest takeaway from the YouTube link that I provided over there on your version. And then last but not least, it says, let's read an article about our moody Earth. Yes, you read that correctly. Earth is as moody as a toddler or a teenager. The article is in a separate OneNote page and is called Hottest Ever. read through the questions before reading the article and answer these as you go. And so it kind of gives you hints as to where you'll find these answers. Okay, so top of page 3, top of page 3, middle and bottom of page 3. Okay, so I'm not going to go through that article because that is definitely something you should do right now. So go ahead and skim through this article and find those answers so you can complete this activity. All right, thank you so much.